Thank you all for coming. Thank you to Buzzwords for having us. It's really, really nice to be back as speakers this time. It's fab. We're from Climate Policy Radar, and as was said, we're going to be talking about building a knowledge graph for climate policy. We're going to go through all of this from end to end, all the way from the sort of foundational concepts that we use in building this knowledge graph, all the way through the process of building the core classifiers up to evaluation, scaling, and show you some results. But we'll start here. Who are we? What's Climate Policy Radar? We are a non-profit organization. We build open databases for climate policy research and tools associated with those databases. We're used by governments, civil society, researchers, the private sector, international organizations to discover, understand, research, analyze the climate policy landscape. We bring together a lot of disconnected, disparate, hard-to-discover sources of information, put them all in one place, and make them discoverable. And in practice, for the time being, that looks like this. We're a search engine. You can come to our web app and type in the word flood, and we'll give you search results about floods, in theory. If you click on one of those results, we'll take you deep inside that document and show you where exactly those terms were mentioned. And this works. We have documents from 200 governments around the world, about 27,500 of those documents, which adds up to 2 million pages, 45 million individual passages of text, which are read by about 350,000 users a year from all over the world who spend a lot of time engaging with this stuff. So that's who we are. That's what we do. It's good. It works. We're used. So why a knowledge graph? Why are we setting out on this big endeavor to build something new? These stats are fine. They're great. They're wonderful. But there's another stat here, another number that betrays something more important, which is this. There's only one way to explore the data at the moment. If you know what you're looking for, it's fantastic. You can dive straight to that point in an individual document or set of documents. But if you're new to the domain and trying to understand the entire landscape of climate policy and how it fits together, or if you're trying to compare two disparate ideas, disconnected ideas, or looking for kind of emerging pathways in the climate policy domain, traditional search kind of falls short. We need a way of being able to move laterally through this collection of documents. In other words, we want to allow users to browse our library of documents. And users tell us that a way that makes sense to them for exploring this dataset is by topic. We might be able to recognize the topics that exist in documents and use those as bridges between those documents that both mention that topic. So let's do that. If we call this an entity or a topic or a concept, we can imagine marking every instance of that topic in the dataset by hand, going through and saying, if this is the concept of floods with this definition, where does it appear? We'll add a little sticker to every passage where it's mentioned. People do this. People do this by hand. Kind of mad. But as data scientists, data engineers, I think we can all probably recognize this as a pretty standard named entity recognition task. We can automate this. We can scale it up and make that process much faster. Again, named entity recognition is fine. It's great. It's well understood. Where does the knowledge graph come into this? I tend to think of knowledge graphs as named entity recognition plus some superstructure, some meta structure for organizing those concepts. A very simple way of illustrating this is to add some hierarchy to those concepts and say that there are broader versions of the concept of flood or more specific versions. So we might mark this subconcept as being a coastal flood, and we can say that every mention that we detect of coastal floods is also an instance of a flood, and every instance of a flood is an instance of an extreme weather event. I hope you can see already from this that by training or developing multiple systems for recognizing each of these concepts, the value of those instance recognitions, those tools, compounds. We get extra value from this just by stacking this superstructure around those concepts and those classifiers. But hierarchies like this are severely limited. The real world, and especially the sort of fast-moving or fast redefining world of climate policy, where there are multiple perspectives, all clashing, people are trying to come to agreement, is very, very difficult to stick into a strict hierarchy like this. Yeah, our users come at us from multiple perspectives and want to see their worldviews represented. To some people, the concept of sea level rise might be a slow onset event. To other people, it might be a marine hazard. Both of those should be encapsulated in our graph, but this kind of strict scheme doesn't allow for that. We also might want to represent the more associative relationships between concepts like deforestation and flooding. There is a link there between those two concepts. You would want to be able to represent that or see that represented. But deforestation isn't a type of flood, and floods aren't a type of deforestation. They're just related. Again, this strict scheme doesn't allow for that. So we allow for more than that. We allow for those more associative relationships to exist between concepts, and allow ourselves to bend and break that hierarchical scheme where it's useful. Because those concepts that are related are also just concepts, the same ontological rules apply, so they can sit in their own hierarchies. And because those other concepts in those other hierarchies are just concepts, the same rules apply, so they can also have those looser, more associative connections between them. And we also allow concepts to sit within multiple hierarchies, to have multiple parents, to allow those multiple perspectives to be represented. And I hope you can already see, just by scaling up this process, adding more and more concepts, a graph begins to emerge. A network with lots and lots of complexity in it. Just a few simple rules allows for a lot of expressivity in the domain modeling. So that's why we build a knowledge graph. We're able to capture a lot of that domain knowledge, a lot of that expertise in a simple scheme. And especially when combined with those individual classifiers for each of those concepts, the value really, really compounds. So we have this sort of intellectual frame for how we might define concepts and how they can be related to each other. How do we actually define those concepts? How do we develop the big list of all of the things that we want to find? At CPR, we rely on humans. We have a team of climate policy experts in-house who we collaborate with very closely. Yeah, there are some modern approaches to knowledge graph building, which are sort of one click, one button, fully hand it over to an LLM, let them define concepts, let them define the relationships between them, which are great for simple domains. But in this sort of high-risk, high-impact domain that we're working in, we don't think that we can abdicate our responsibility for our institutional perspective to an LLM. We want to take responsibility for the way that we see, categorize the world. As we heard in the keynote this morning, the power to name who gets to make the decisions about the concepts that are important is a very important decision in and of itself. Doing it this way, relying on human expertise, allows us to define underrepresented concepts, things that an unsupervised method might not emphasize or might not see the importance of in the scheme. For example, underrepresented groups. It's very important for climate policy analysts to understand the implications of a policy decision on particular underrepresented or underserved communities, but they're very rarely mentioned in climate policy documents. Being able to manually say, this is an important concept to us, and wrap that with a classifier is useful. How do we store these concepts? Wikibase. We have lent on Wikibase, or the wiki community, the wiki world, because it's a fantastic example of building this sort of structured, large-scale knowledge at massive scale. Wikidata have done this for a decade with millions of nodes, billions of edges between all of these concepts in a very open, transparent, discursive, auditable way, which are all things that we aspire to be. And by using their technology, by using Wikibase, which is Wikidata with no data in it, we are allowed to populate our own instance. By using that technology, we also inherit a bunch of community norms for our climate policy experts to have those discussions, to check each other's work, to disagree and agree, which has really helped. So we're using Wikibase. This is what a concept looks like in our concept store. This is the concept of a flood. It comes with a short description, a set of aliases, a longer definition with links to authoritative sources, and a bunch of relationships to other concepts in the database. And letting our policy team loose on Wikibase for about a year, we've ended up with this, which is our start, our first attempt at a map of climate policy. These are about 1,500 concepts, arranged according to those relationships, both hierarchical and non-hierarchical. Still tons of complexity yet to be defined in here, but this is a pretty good start. So those are concepts. We can now structure that expert perspective on the climate policy domain, but we want to scale this up. We want to not only go through manually adding stickers to PDFs, we want to run modern NER, which involves classifiers. This is a little illustrative. I hope it's descriptive enough of the way that this works. If this is our concept store, we can pull concepts out of there as structured data, store it in Python as nicely validated objects. For example, this, again, is our concept of floods. We pass those concepts into what we call a classifier factory that, based on the attributes of that concept, the complexity of it, the amount of data that we have, spits out a classifier that contains that concept. So it's a one-to-one relationship between concept and classifier. For this example of floods, maybe we output a keyword classifier that is just a fancy regex. It's simple. We can just look for a few keywords, run it very, very fast. But because this is a factory, it has some kind of intelligence or nuance built into it, we can maybe recognize the situations where we need a more sophisticated classifier, like a BERT-based model or a spacey classifier. Or in even more complicated situations, maybe we lean on an LLM or some other magic, special, fancy classifier that is yet to be invented. The point here is that there is a separation of concerns. We've decoupled the policy research from the data science work to define these concepts, or classifiers, sorry. Policy can focus on accurately describing the climate policy domain, all of the relationships between these concepts, and we, as data scientists, can keep our focus on translating that data into classifiers that we can deploy at scale. In general, we try to use the smallest possible models that deliver the best possible performance. We do that somewhat for ideological reasons. We want to minimize the negative climate impacts of our work while maximizing the utility to our users. But it's also a strategic choice as well as an ideological one. Smaller models are often much more interpretable, easier to debug. The policy team themselves find it very easy to debug problems going on with keyword-based classifiers because their mechanism internally is so straightforward. We also don't want to end up in a situation where the tail is wagging the dog, and we're defining super sophisticated, complicated classifiers just based on hype. We've discovered that in a lot of cases, the regex-based models are just as good as the LLMs, and in those situations, it makes sense to use the tiny model. So that's classifiers. Evaluation. How do we figure out whether these classifiers are producing reasonable results? It might surprise you to hear that, again, we rely on human expertise here. Again, we don't think that we can abdicate our responsibility for understanding our work to LLMs. So each model is checked against the annotations of multiple human experts. We give those experts, or they have already, access to the definitions from the concept store, so exactly the same data as the classifiers see. And we ask them to go through a few hundred passages and mark where they spot instances of those concepts. We quite carefully sample the passages that we're going to expose our internal users to, or experts to, so that we're not wasting their time. Their time is valuable. We have thousands of concepts to run through. We don't want to send them off labeling lots of low-value, low-quality examples. Also, the careful sampling that we do, the fact that we have invested time there, means that we can pay attention to more than just overall classifier performance. When we have that data set of gold standard ground truth labels, we can measure the overall performance, but we can look at the performance on multiple substrata, subgroups of our data set that we care about. As I said at the beginning, we have documents from all over the world, and we want to make sure that we're not biasing towards higher performance on certain regions of the world. So we stratify across region and measure the performance, make sure that it's roughly consistent. We want it to be good, but also even. We also, the very first step in our process after PDF parsing is translation. We get documents in almost every language. We want to make sure that we're not biasing towards documents that were written originally in English. So we measure the performance on both translated and non-translated text. And we also have lots of different document types. We have law, policy, corporate disclosures, litigation, all sorts of stuff. And we want to make sure that we're not subject to weird effects in domain shifts. As language shifts from one domain to another, we want to make sure that our classifiers perform evenly across those. So we can come up with a whole raft of quantitative metrics here. But we know as data people, data scientists, data engineers, that metrics are really just proxies for human preference. And are lossy proxies at that. They're not always perfect. So in addition to running those quantitative checks, we also run a qualitative vibe check. We've built a little tool that we call the vibe checker that exposes the policy team to a nice long list of mentions that we've picked out of the dataset to make sure that the metrics that we're seeing are kind of aligned with their subjective view, that the things that we're picking out are in line with the original definition that they entered into the concept store. Ultimately, we'd like to do away with this. We would like the quantitative and qualitative checks to be aligned enough that we can get rid of the qualitative check and, again, reduce the burden of work on the policy team, give them more time to go and define more concepts or add more relationships between them. But for now, while we're still in this growth phase for the knowledge graph, this has been a really useful tool. So that's evaluation. At this point, we have a scheme for defining concepts that are important to the climate policy domain, a way of building classifiers around those concepts, and a way of making sure that those classifiers are performing as we'd like them to. But all of that is the easy part. I'm now going to hand over to Fred, who's going to talk about how we scaled this to all 40 million of those passages.
Thank you. Thanks, Harrison. Hello. I'm Fred, as mentioned. I'm the tech lead of the platform team at Climate Policy Radar. We are responsible for the underlying structures. So a key concern for us is data processing and the scalability in terms of resilience, developer experience, validity of that data processing. So I'm going to give you a bit of an insight into what we've been building, the challenges, the achievements we've done so far. We feel like we're at the foot of the mountain, like we've come a long way, but also we look ahead and we're like, there's quite a lot of stuff we need to do and we want to do. So I'm going to give a little bit of an insight into that as well. And I'm sure stuff will come up in the questions as well. This is how our pipeline for this exists today. We want to relate those knowledge graph concepts to documents. And essentially, we're talking about a text classification pipeline. You can see over here, classifiers are trained based on concepts and labels, and the tools Harrison's already mentioned, Wikibase especially, where the concepts are defined. Having built classifiers, trained classifiers, we aggregate, we run inference on all of our passages, aggregate the results, and index them into our search database, which we're using Vespa, you might have heard of. And then there's some separate surfacing of concept information that happens alongside that. So how do we scale training? Let's start at this end of that pipeline and ask this question. And the key thing I want to say is that if you want to build a car, you need a production line. We have focused on having a factory for classifiers because we want well over 1,000 very soon. And that's going to keep going up as well. We've not got a point where we're like, oh yeah, we'll get to this number and we'll be happy. We currently have 1,500 concepts ready to have classifiers built for them. We need to think about how we manage the process. So currently training is very dynamic. That policy team define a concept. The data scientists work on thinking about the model, the parameters, the source data changes, the metrics we want to use change, the way that the models get promoted through environments, and the way that we track them all needs to be very repeatable and very low cognitive load. Our factory today to abstract those details is a CLI. This means simply running a few commands, lets us grab a concept, train a concept, evaluate a concept. This tooling has got us to 80 classifiers, which is a good start. And I think 74 of those are actually live in production. The others are very nearly there. Taking this to go to thousands, we want to move to more of a pipeline approach around this, where automatic data can be automatically picked up on as it's new, retrained, checked against metrics, promoted through environments, and that can just happen on a schedule. At the moment, this is often run locally, which means that we're bottlenecking compute, and also makes it harder to avoid siloing metrics. So we'll hopefully, in not too long, be in a better place with that. But that's just where we want to keep pressing up the mountain on. Moving on, inference and indexing. Scaling these has been quite an interesting challenge. It's had lots of fun problems to solve. Applying all of the classifications to all of our passages at scale has reminded me of something called the weight calculation. There's probably a statistic likelihood that there are some former physicists in the room, and also just general nerds who know about science fiction and space travel. The weight calculation is the idea that if you were to set off today in a spaceship to go to a distant star, to set up a colony on a distant planet, with today's technology and understanding, you could be overtaken by a future generation of humans who have developed in their ability to make space travel faster. This very much happened to us. in some of our earlier attempts to build the pipeline, we realized that they needed to be iterated on. The example of this is just the indexing for one of our first drafts. We sat down and were like, OK, so if this takes this long, how long will this take? And we worked out it would take 137 days to run over all of our data, which is just completely not acceptable. So we went back to the drawing board. We let our technology and our understanding in our code base develop. And pleased to say it now takes less than a day to run over our whole corpus. And we're still improving on that as well. I want to just touch on two areas that we saw those gains coming from, that we achieved the scale in terms of like the speed and efficiency that we were after. And that's concurrency and better looping logic. Concurrency version 1. Each of these lines represent a document and essentially a batch job running indexing. We knew that we needed concurrency, so our first attempt to do that was to set up something that ran in batches. But you can see the problem. I like to call the problem the background. There's these long bars. Some of our like 2,000-page long documents take a very long time to index. And then there are these short ones, but we wait until the end to start a new batch. So it didn't take us long to realize we needed to do this, a more interleaved approach, where new batches, new documents start as soon as they're ready to. You can still see some of the background, but I'm not too worried about that. There's some cold start, some async blocking. There's some little things that I don't expect to have as big an impact. But having this not only means that we're now twice as fast, it also means we can scale more predictably. So previously, the CPU impact on Vespa of that batched approach was very spiky at the start and then petered off, which kind of is not what you want. You want something much more predictable. So this is very much more level. We know how wide we can go, and we can do that accordingly. The other area that we had to move away from was thinking about this as a problem of running a classifier on a document. And that worked really well when we had one classifier. But as soon as we had two classifiers, we were suddenly running a classifier, a document, a classifier, the same document, which doubled our runtime. It didn't take us that long to realize that this won't be sustainable long term. So simply aggregating, making a step that we bring together all of the concepts before we load them into Vespa, again, was a huge, huge time save. So those are the main ones, and pleased to say that now the whole pipeline takes less than a day. We have some more stuff we want to do around being more incremental, more micro-batching. That's still to come. Let me talk about observability. And at this point, I want to share with you an embarrassing story about my own personal lack of observability. I went to the cinema recently, and I was rushing. So I missed dinner, and I wanted something to eat during the film. My local cinema has just opened a pizza van inside the cinema. You can get a pizza ordered to your seat, which seems like a really good idea. Unfortunately, I missed some important information in the process of ordering this pizza that led to something quite embarrassing. When I arrived, there was no one there. There was no pizzas on display. There was no other customers. I went straight to the front, feeling like I got lucky and asked for a pizza. But I didn't have a chance to stop and look like, how big are these pizzas? What do these pizzas look like? So that's warning sign or clue I missed, number one. I then ordered it, and the person who took my order was really surprised that it was just me and my friend that wanted a pizza. So I just thought, oh, that was odd. Brushed it off, moved on. I came to pay, and it was really expensive. And my mind went to cinemas. They're always marking up the price. How ridiculous is this? Anyway, they agreed to take to my seat. I went and sat down right in the middle of a very crowded cinema. 10 minutes into the film, emerging from the side was the biggest pizza I've ever seen in my life, and being struggled to carry into the screen by these people who were asking people, is this your pizza? And everyone in the cinema completely distracted, focusing on the pizza, and I had to be like, yes, this is my pizza, I'm so sorry. I couldn't even open it without it blocking the screen from everyone. I was so self-conscious. And I'm pleased to say my family ate pizza for the rest of the week. Now, I missed opportunities, and in much the same way in a pipeline, we need to make it really, really hard to miss those clues that could lead to catastrophe. That idea of picking up on issues early has become a key principle for our designs and also for my personal trips to the cinema. By the way, it turns out you're only supposed to order a slice. I ordered 12 slices, basically. I essentially ordered 12 pizzas. So this is how we think about observability in our pipeline. We collect all the failures. We try to balance logging to maximize the right information without the noise. And we surface reports at the end of each step. These also alert on Slack immediately if there are any potential issues, if a document failed, if a classifier failed. And we deliberately set this up to be interoperable as well. So you can grab that as a JSON object. We want to work on, still to go is actually like using that JSON object in a data lake or in our observability tools, so you can see a run of all of the pipelines that used a classifier, a set of documents. You can track the lineage through, and deliberately trying to make that something for non-technical users as well, so that policy team aren't blocked from saying, hey, what happened to the floods classifier? Why isn't that showing up? It's like, oh, well, let's check the dashboard. So that's still to come. And we'll be kind of iterating and improving on that further. So in conclusion, on scaling, if you want lots of classifiers, you need to build a factory. Pipelines can go faster as they're iterated on. Don't miss warning signs. Make it hard to embarrass yourself. Let me sum up by going through some of the results of this. You saw those front-end visuals earlier in the talk. As of this week, we've just started launching a new functionality where we can explore documents using this knowledge graph, these concepts. We now have the ability to select, when searching for floods, specifically indigenous people. Find the documents, the policy documents that relate to that. To get information at the document level about what concepts are touched on and discussed in the document, and also to then review specific passages that are to do with floods and indigenous people. So hopefully that's the tip of the iceberg of the potential, and this is kind of our first release of this. We want to go further. There's lots more we've already touched on that we'll be working on next. We like to work in the open. This is the Wikibase URL to our knowledge graph, where you can see all the concepts. This is our code for our knowledge graph, warts and all. Again, we like to work in the open. And this is our career page. We like working with people, if you like the sound of us, and also the 4-day work week that we have. Come and see our careers page. Come and hang out with us. But that's the end of the presentation. We have some time for questions. Thank you very much.
Apart from mentioning the pizza, just at the lunchtime, I guess everything was amazing. We can probably start with the in-person questions, while we also have some online questions. So, okay, first question.
Yes, hello. Thanks for the talk. It was really interesting. So you mentioned the classification and the wiki that you have with concepts that are defined and all that. They resemble a lot with Wikidata. And the question is, what's the connection with Wikidata, and why not improving Wikidata with that? Yeah.
Really good question. It is a very good question. Wikidata has a lot of information in it, kind of overwhelming. We have ambitions to connect up our document sets and our sets of concepts with Wikidata as a kind of bridge between different controlled vocabularies or ontologies, taxonomies. But again, I think it's important that we do have an institutional perspective. Our policy team are now effectively trained Wikimedians. They know how to use this technology. They can go and update Wikidata, and we can push our concepts to either resolved entities, the matching concepts in Wikidata. But again, yeah, I think it's important that we do have a source of truth for our perspective, and that we not be ambiguous about that. I hope that answers the question. But yeah, we have ambitions to be more interleaved with Wiki.
They're also our heroes. Like,
yeah.
We love them. So,
fantastic.
yeah.
The Wiki-based instance that we're using is provided for free by Wikimedia Deutschland. They're fantastic. We met them here last year. Wonderful. It's been really nice working with them.
Okay, I would probably bring in one online question while people brew on more questions. So what type of edges need to be supported? For example, is not a synonym, etc. kind of relationships?
Again, really good question. We have made a very deliberate choice to keep our ontology, our schema, our set of relationships very, very simple. So there are 3 types of relationships that concepts can have, effectively just 2. Something can be or can have a subconcept. It can have a parent concept. Effectively, they're the same thing. And things can be related to one another. We don't specify any types on those related relationships. We've talked about it, but my experience, I spent a lot of time working in libraries, museums. My experience is that over-specifying too early can really paint you into a corner. It makes things very, very difficult to scale. We're already starting to see those types or subtypes of related relationships appearing. For example, we think that one of the first types that we might add in the future is causal, that something causes, deforestation causes flooding, or flooding is caused by deforestation. There is the potential for that kind of stuff, but we don't want to over-specify too early and set up types of relationships that we end up not using or using in one place, complicating our development. Keeping it generic for now has been really, really powerful.
Perfect. Do we have any more questions? Okay. I am tossed between kind of, we have a lot of online questions. I don't know if you want to answer them later because we're very close
People
to lunchtime.
Feel free to get in touch online. We're in the open. Feel free to keep the conversation going either in person or on the internet.
Yeah, thanks. Great for the talk. Thanks for all the information. You mentioned about 80 classifiers. So that's quite a lot. But you mentioned also that you have more concepts. So are you taking an approach to use one classifier for 2, 3, 4 concepts, or just taking one concept and one classifier?
Yeah, there's... do you want to talk to this?
No, you go.
I am so glad that we're doing one classifier, one concept. It makes scaling it so much simpler. And I have a theory that this is where we would have ended up inevitably if we just kept iterating and optimizing anyway. You can imagine if you've got 2 classifiers that each, or let's say one, that's very good at 10 classes, and you want to improve all of those classes. You make a change, 5 have improved, the other 5 have gotten worse. The logical thing in that situation is to now have 2 classifiers, and only do 5 each. And ending up at a one-to-one mapping, even for classifiers that might have a lot of overlap, makes the pipeline downstream so much easier to work with. We can be very thoughtful about our evaluation and the different the ability to customize with different models, different parameters, etc.
Okay, can we take one more question? Yeah, is it okay? I would like to take one more question from the online audience. And, so the question is about maybe your architectural choices. Since you're using Vespa, do you embed encode each sentence separately as climate policies are structured? Do you use metadata to store chapters, titles, etc.? Is there a reason you use Vespa instead of, I'm assuming this question is from Superlinked, instead of which supports structured documents more naturally, but just about your choice about using Vespa, maybe
yeah,
you can
great.
enlighten us.
Quite a few questions in there. I guess I can speak to some. And, so yes, we do use Vespa. We index titles. We have a document index and a passage index because some information is only available at the document level, others more at the passage level. I've never been particularly opinionated about tools. I think it's always more important about like how you use a tool. So I do have a lot of things I really like about Vespa, like especially like the developer experience. I think is quite nice. It's doing what we need it to do. I think that'll probably be my main comments. So.
That is perfect. I would say that no rush. We're closest to the lunch hall. And thanks once again to Fred and Harrison for amazing talk. And they're going to be around if you have more questions, catch them while they're having lunch. And I will relay all the questions that we have received online. They will be answered. I will pass on the questions to them. And thank you so much for joining. And let's thank them with a round of applause.
Thank you very much.
Thank you.